Today we're going to talk some more about beam deflection, really just work some examples of beam deflection, and I guess we'll talk about it as we do that. And then we'll also talk about initiating our Truss project, so the bigger project that you will work on periodically from now until the end of the quarter. We'll do that at the end of the stream. We'll start out with just beam deflections. So I've had several questions about beam deflections. So particularly the web work problems, they are on exam 3. You know, there's maybe two problems that are related to beam deflection on exam 3. So I thought I'd work some of them. There are some tricky ones or not even tricky. They're just, you got to think about it. And there are some parts to them that are tricky. I know we can work one of these. I don't know how much time we want to spend on them, but if there's a particular one you want to see, then let me know. The one I plan to do is this one. This is problem 4. So it looks pretty simple. It's got a distributed load and a point load and a little cantilever section, so that doesn't seem too bad. It's got 6 parts to it, so there's quite a bit to do. But, you know, it doesn't look like there's too much loading. But there's some subtle pieces to this one that make it a good bit more complicated than it first seems like. And it starts out actually pretty straightforward. We'll work through the beginning here without too much trouble. All right, why don't we copy this first of all? Get all of this. I don't guess we need the little boxes there, do we? Just need that part. Oh, I haven't opened OneNote. Hold on. Let's look at the record here for a while I get OneNote going. Let's see, we need a new sheet and we need these things to be on. That's probably all. Yeah, that looks good. All right. So let's paste our problem statement in here. Here it goes. We can enlarge it a little bit. So we've got a W beam. So the W are wide flanged I-beam. So this is an I-beam shape. It's an 8 by 15. So that tells us, and these units here tell us that we're in US customary units. It's structural steel. That'll give us information about the modulus of elasticity. We'll need that since we're doing deflection. Neglecting the effect of self-weight. That's our assumption. Unless we're specifically told to include self-weight, our assumption is that we're going to neglect self-weight. This one specifically tells us to neglect it. All right, so first part, A, the deflection of the beam midway between the supports. Okay, so we have we're going to need our reference sheets, aren't we? Let's see. We're going to need the ones that have our beam equations on it. There they are. So we have a case 5, a offset or eccentric point load, and a case 7 distributed load. Now our beam actually has this little cantilevered section CD that since we're neglecting self-weight, it's not doing anything to the span between point A and C, the pin and the roller. Now if it had self-weight, and that would be a distributed load out here, we'd have to figure out, well, it's actually going to make the middle of the beam sag a little bit less because this cantilevered section is pulling it back up. So, but we're neglecting that, so we're not using it. So what we are using is, let's do the easiest part first, which is just a simply supported beam, ignoring the cantilever, with a distributed load all the way across it, and we want to know the deflection midway between the supports. So case 7, deflection, this is at x equals L over 2. That's midway between the supports. L is the distance between the supports. So we have just this equation, 5W L to the 4th over 384 EI. I have MathCAD open, so we're going to need it later. So let's go ahead and use it for this also. Forgot my equation. 5W L to the 4th. 5 times W times, well, let's use capital L to the 4th over, I think it's 384 times E time, whoa, we don't need that R in there. Let's make sure that's right. 384 EI, yep. Now we got to define these things for our beam. So W for me is, where's it at? 17 pounds per foot, right there. Now in MathCAD I had to tell it these are foot pounds instead of pound mass. L is A plus B, which we'll have to put in A plus B. 6.4 and 8. All right, so A plus B, where A is 6.4 feet and B is 8 feet. E, it said it was structural steel. So E for structural steel is 29 in the US units, 29 million PSI. I will have to figure that out. It was a W8 by 15, I think it said. So that means we can look it up. There it is, W8 by 15. So let's see where our W beams are. There's S, W. So we're looking at this column here. And we're looking for 8 by 15. We're looking 48, and the units on that are inches to the fourth. So 48 inches to the fourth power. Okay, and then this, we can set this equation equal to y1, I guess. And let's see what it equals in inches. So probably need more inches, or more decimals than that. There we go. So this, 12 thousandths of an inch is the deflection at the center of the span from just the distributed load. So that's part of it. We also have this point load, F, to deal with. It's eccentric, it's not in the center. So there are two cases in our reference sheets for point loads. These two, 5 and 6. 6 is a point load right in the middle, which is not what we have. 5 is an eccentric point load. In the picture here, we have to be careful with this case because it specifies that B has to be less than A. And even the equation over the elastic curve says that this equation is only good between 0 and A, so only good for this little section over here. Now in this case, we just want the center, so we have an equation that is the deflection at the center without having to do any of the elastic curve or anything like that. So we can get this number. P is where we'll have to try and let's do this. Do that, or else I'll never flip back and forth enough to remember it. So Y2 is, now these are negative. I'm leaving the negative sign off for right now. So technically I'm making deflections that are curving upwards, but I know they actually are negative. So you could put the negative sign on there if you wanted to. P times B times 3 capital L squared minus, oh, you know what? Oh yeah, I did put a value for L. Okay. L is that one that if you don't put a value in there, it'll go along with it, but it thinks it's liters. It thinks it's the units of liters, so you have to be careful with it. B squared, all of this over 48EI. So most of this we already have, but it's telling us we don't have a value for P, so let's put P equals, what they call it F here, 403 pounds. And we have B, we have everything else. Let's see what that evaluates to. And then let's put more decimals. All right. And we should have Y at the center of the span, not the center of the length of the beam, because the beam has that cantilevered section, but the center of the span is equal to Y1 plus Y2. In inches, that is, with more decimals, 04. I wonder if I can copy this number and paste it into WebWork. Let's see, where did WebWork go? Here it is. That one. Hey, I can. That was in inches, but it's negative. So let's put a negative sign in front of it. And let's see. we are correct. No, well, we're really close. And I copied it directly out of MathCAD. So not sure what's going on here, but we are off by, wow, what, 5/10,000ths? Is that what we're off by? We have 42042,339, 04238. Yeah, so we're off right there somehow. I don't think we typed anything in wrong unless there's some hidden decimals in some of these numbers that we can't see. I don't know why we would be off. This doesn't say anything that we're in a different gravitational field, so our pound force should be correct. I don't know. I don't know why we're off. Unless it's not using 29 million for steel's modulus of elasticity, but that is what the book has for modulus of elasticity for structural steel. So for some reason, WebWork doesn't like this number, but I like it. So if you're having trouble with that, you know, in these WebWork problems, when you're pretty sure you're doing it right, maybe you even are putting it in MathCAD, so you're not rounding at all, then you can click in WebWork, email instructor down here, and it'll send me your problem set with your numbers and what it's expecting, and then I can easily look and see if it's the same thing like we've got here where we're off by 5/10,000ths and it doesn't like it. And so that's a thing, and not even a whole 5/10,000ths. I mean, it's tiny differences. I'm not sure why it's being so picky on that, but it is. So let's carry on. Let's go here. All right, so I'm going to say this one is good. Part B, the slope of the beam at point C. Now, you going back to that, you don't have the luxury of seeing the correct answer. So if you're pretty certain, or even if you're not quite certain but you think you're right, it doesn't take long for me to check your answers and see if they are something like this silliness. Slope of the beam at C. So right here, over the roller, we want to know how much this beam is sloping upwards. So we assume that it's doing something like this. Let's see if I can, something like that. And we want to know this slope right there. And so there's two things contributing to that slope, the point load and the distributed load. The distributed load is the simplest one because it matches our case. As long as we're thinking of just the beam between the pin and roller and ignoring this cantilever part right now. So we need our references. Where'd they go? They're in here, but over here. So here we are, case 7. Theta 2. Now in this case, theta 1 and theta 2, they're the exact same thing. Just one is positive, one is negative, based on where they're measuring the angle from. So we'll use WL. We'll copy this and put it over. Oh wait, no, we needed MathCAD. So here, I guess we can put it over kind of lined up with these others. Okay, so we'll say this is theta 1. And that equals W times L cubed over 24 times E times I. This one should not have units because it's going to come out in radians. So we get a small number. That seems reasonable. Now the point load. We have to be careful with this one because we're in an eccentric point load where it's not centered. And so we've got two different values. They're not just positive and negative of the same thing. They look similar, but there's a b squared and an a squared. So they're not just the same thing. So in this case, we've got to look at the configuration in the picture here, which is mirrored from what we actually have. We actually have the point load. I did check. A is smaller than B. So our image that we are dealing with is mirrored from this one. So we want the slope that's further away from the point load, right? So here's the point load right here, and we want the slope further away from it compared to this one. So in this picture, that is theta 1. So we want this angle for our slope at the end of the beam. So we're going to call this theta 2, and it equals, again, I know that these are both making the beam slope in the same direction, so I'm going to just keep them as the same sign, which I made a positive sign on the first one, so I'll make a positive sign on this one too. Even though this says negative in the equation that I copied here, but that's referencing a different coordinate system. P times B times L squared minus B squared over 6 times L times E times I equals, and there's our small little deflection, theta total, or this is at C, right? So theta at C is theta 1 plus, whoa, we got some crazy stuff, theta 2 equals, let's turn this in, whoops, this into a decimal with a bunch of decimal places, copy it, see if WebWork likes this one by any chance. Here you are. I don't know if I need to put radians on here, or we'll see. Oh, no, it doesn't like radians. We do have the right number. Again, we're off a little bit. We have 77 and they have 73, so I'm not sure where the discrepancy is in this problem, but there's something that is consistently off between the way this problem is solving and MathCAD is solving. And I wonder if there is, like this 17 is actually supposed to be 17.2, or you know, if there's some, or 16.8. I wonder if there's something rounded in one of these numbers that is not being shown to me, because we're consistently off with all these, even though we are not rounding anything. It apparently doesn't like radians as a unit. Still doesn't like our answer, but because it is different. I mean, it's still a tiny, tiny number, but somehow we're consistently off, and I'm not exactly sure how yet. But that's where we're at. Let's see. What's the next part? The deflection of the beam at point D. So I could see, and I have had questions about this particular problem. It could be that there's a tiny error somewhere in this problem, and you're just not going to get it right without sending me the your question about your problem, and then I can look and see where you're off, because I don't think we did anything wrong in those problems, those two solutions, and we're still getting them wrong. And we're not doing anything except in MathCAD. All right, deflection of the beam at point D. So that's this beam. We've kind of done that before. That is where you take the slope at C. So we take, you know, this angle that we've got, and we treat, we assume it's a small angle, which it was. It was either way, whether we were correct or WebWork was correct. It's a small, you know, 0.007 radians. No, 0.007. Oh wait, is that a problem? No, they had 3 zeros. Super tiny degrees, or radians in this case, also super tiny degrees. And as long as it's a very small angle like that, then we can approximate this deflection by just taking the distance CD in this case and multiplying by theta. I called it theta C, I think. So if we just take our theta C and multiply times the distance C, 5.4 feet, that should give us that deflection, how far that cantilever part is kicked upwards. So 5.4 feet for C. Let's add that to our list up here. And if anybody sees where I've made an error, maybe I've typed something in that I don't notice, let me know, but I'm not seeing it. All right, so y at D is equal to theta at C, I didn't make that a subscript, times C. I'll put it in inches, more decimals, and let's see if we by any chance get this one right. Still not, it's a very tiny number. That's another problem with web work and tiny numbers, is that they don't get along very well. But let's see. And this would go upward, so it really would be positive, and I had it in inches. Yeah, it doesn't like that. And see, we're getting a little bit further off here. Now we're off by 300ths. So, you know, maybe, I don't know. I'm kind of suspecting that one of these numbers should be displaying a decimal of some sort, and it's not. That's what I'm kind of beginning to wonder there. In a second, maybe we'll go into the actual problem statement and see if I don't want to dig through that. It's a bunch of code. But we'll, I don't know. We'll carry on for now. We're doing it the right way. All right, now starts getting a little bit more tricky. The deflection of the beam at point B. Okay, so now we have to start using some equation of the elastic curve. I don't think our references give us the deflection right under the point load. They do not. We'd have to put our values in to calculate that. So we're going to need, let's do the distributed load first. It's easiest again. So there's our equation of the elastic curve for the distributed load. And now we'll have, I guess I can just keep redefining these things. Y1 of X is this equation. P times X over 48 times E times I times 3 times L squared minus 4x squared. Okay, so that just put it in as a equation as a function of x, where we want, it said the, oh, I didn't put them in here. It said that we want the deflection at point B, which is right under the point load, which is a distance of A. So if we put in A equals X for the distributed load, we should get its contribution to the deflection. So Y1 of A is that distance. And again, it's actually a negative because it's slope, or it's deflecting downwards. So there's that part. Now the next one, this is the eccentric point load. That's this equation, and it has a very special qualification on it. I'm going to copy that too. It is only good between 0 and A, according to this picture, where A is the longer side of the beam, and it's only good from that support to the point load on the longer side. And ours is mirrored from that. So we have to, you know, make sure that we're putting the right numbers in when we do this. So we're going to put in, for X in our equation, we're going to put in the distance. This one may not be obvious which way X is measured from, but X is measured from the left end going to the right. So that means I need to put in a value of A, or, well, in this one, in this picture, A. In this picture, B, because this is mirrored from what I actually have. So I need the distance from the support to the point load, but on the longer side, so BC instead of AB. So the eccentric point loads are really tricky to deal with. So I'm going to put in the equation, but I'm going to put in what I have labeled as B as the value for X once we get to that. So here's our equation. And we'll do Y2 of X is equal to P times, now here, this B, this is probably going to be another place I could mess up. B in this picture refers to the shorter distance, not the one on the right, or it's not that. It is specifically saying that B is less than A. It's the shorter distance. I put way up here, well, not on this one, I guess, on here, the variable A is the shorter distance. So what I have A and B, the equation have A and B, has A and B, but they're opposite of one another because of the way the beam is mirrored from the reference sheet. So I need to put an A here. It would have been much simpler, or less confusing, to redraw this thing, and instead of using the A and B variables that they have here, just put B over here because it's the shorter distance, and A over here. And that might be a little clearer when you are looking at this of why you're switching A's and B's, and it just doesn't make sense. There's another B, so I need, whoops, I don't need it in the exponent though. So I need this B to actually be the variable A. Oh, I missed it. X is still a variable, so that's fine. Okay, and then Y2, I want to evaluate Y2 at, well, let's look at our reference, at the distance from the support to the point load, which in this picture looks like A, but it's the longer side. From here to the point load is the longer side. I have the longer side labeled as B. So same thing there, where I have to do the opposite of what it looks like I have to do. And it would be a negative value. I just have a positive value on here. All right, so the total, Y total, this is at, is this maximum? What is this? Oh, this is at point B. So Y at B equals Y1A plus Y2 at B. What's that in inches? More decimals, please. Let's copy that and see if by any chance WebWork thinks this is a good number. Oh, whoa, something is definitely off here. 04. I probably made an error. Let's see what it did. First of all, let's make sure I've got everything correct there. This is very blurry, so it's kind of hard to tell, but those did get translated correct. Both of these should be bending the beam downwards, so that seems okay. Like that they're the same sign is what I mean. But somehow we're getting very different numbers. So let's see. The distributed load, there's no trick to it. Now technically it does show on our reference sheet a range. It is only good from x equals 0 to x equals L over 2. But basically that's just the beam is a mirror image from left to right. So you can cover the whole beam. Just this particular form of the equation only really works for 1/2 of the beam. But that seems okay. And in this case, let's see. I might have put the wrong value in for what I needed to measure here. Let's see. So I wanted the deflection of the beam at point B, so I should have put in a value of A for the distance. What did I put in? I did put in A. No, this is it right here. I did put in A. Yeah, I did put in A. Okay, so that's not the problem. let's check this guy again. Make sure we didn't make some error after I explained it over and over again. Maybe I typed something wrong. So this is the eccentric load, this guy. The equation I have here is only good on the longer side of the beam. The longer side of the beam is a distance from the support to the point load. It will give me that equation. It says, or it will give me that value. It says, and for me that longer distance is B. So it's that distance, and B is 8 feet. But when I plug in, oh, but I put A's in here. Why did I put A's in here? Oh, because for me, oh, wait a second. All right, maybe I confused my own self. so B is the longer distance. Okay, that's what I did wrong. I was supposed to put, it says B here, so that's fine, but I did put B in. It's right there. I switched these to A because B in the picture here is the short distance. My setup has A as the short distance. But then when I evaluate the equation, I put a value for B in, which is the long distance, which is where I wanted to solve it. Then I added them together. Did I add them right? A and Y2B. I get a very different. They had 04, I believe, here. Yeah, 042, and I have 06. That seems very different. This problem could have lots of issues with it, or I am missing something entirely that I don't see at all. So, and you would think that if I were having like type something in the equation wrong, that I wouldn't get the right units out, because MathCAD does track units. So I'm pretty sure that the exponents are all correct and the types of numbers are in there correct. That is a 6 EIL, 48 EI. That's right. So I don't know. It doesn't seem like there's an obvious thing going on here, but something is clearly creating problems. I don't know. Let's move. These are the ways to do this. I'm not sure why WebWork is disagreeing with me right now. Let's carry on, and maybe I'll see something happen shortly. But right now I don't see it. What else does it want? Part E and F. These are tricky. All right. The location on the beam relative to point A of maximum downward deflection. So this is not an equation at all. We have the equation. We have the equation of the elastic curve, but we have two things going on: the distributed load and the point load. And we can't just take, like, they do have, where's it at? They do have Y max for each of them, but we can't, well, that's not both of them. This one, I wonder if I got the wrong equation. That looks what I did. I might have, oh, I did, didn't I? For the distributed load, I have the wrong equation. I have the one that matches up with the point load in the middle. That's what's wrong. We can fix that. Let's go back to that. That's the problem. I grabbed this equation, which is a point load in the center, but we have a distributed load all the way across it, so we should have done that. That one, we can figure that out. Sorry about that. So WX, I should have known that it had a P in it. It's a point load, not a W. 24 EI X cubed. Let's get rid of all that. It's messing me up. X cubed minus 2 times L times x squared, x squared, plus L cubed. There's a 4. We might actually get one right. Let's see. And it is negative in their coordinate system, so we need to put a negative on there. Oh, I didn't put inches on it. Come on. Hey, we got one right. All right, excellent. I was wondering what was going on, but I had just copied the wrong equation down. That's an easy mistake to make, particularly when you're on computer screens and you're sliding back and forth and all that kind of stuff. I would definitely, if you're taking an exam, definitely recommend either using your book and the charts, the written charts, or if you're not using your book, then print the charts out so that you have them on paper so that you don't get that kind of mistake going on like I did. All right, now back to this thing. So what happens here is we don't have an equation that is going to give us the maximum deflection for these two combined. We have two equations that give us their individual maximum deflections, but they're not at the same spot. In fact, it probably says that in the reference. So here, y max, we have a maximum equation, and here's the location. And then here, we have a maximum deflection, and here's the location. And this location, L over 2, does not match this location, square root of L squared minus B squared over 3. So we can't just add them together because they're at different locations. So instead, we have to use the equation of the elastic curve for both of these, this one and this one, and add them together to figure out the shape of the beam. And we got a couple of routes we can go. I'm going to do graphical. WebWorks already disagreeing with me anyway, so we'll definitely be disagreed with this way with WebWork. You could do calculus, so you have the equation, or the two equations, you add them together, that's the superposition part, and then take their derivative, set it to 0, and find the max or min, in this case, I guess, because it's actually a negative point. And figure out the location of the deflection at that way. The only issue, which is totally fine, both of those are totally fine ways to do it, except this equation is going to give us some problems because this equation is the mirror of what we actually need. So we have the mirror image of this. Ours has the point load closer to the left side versus this one closer to the right side. So we have the mirror image. So when we use this equation, if we use it as it is, then this value x will start, it's going to start on the opposite side of where we need it to start. So we can't just copy the equation directly. We have to modify the equation a little bit to mirror it. And how we're going to do that is like this. Let's go back to MathCAD. So here's the equation right here, in fact. It was fine here because we weren't really, we weren't trying to add every point of the equation together. We just wanted a single point, and we got that same point and added them together. Now, in one of them it's at A, and one of them it's at B. But those were equivalent to the same point, and that's kind of the mirror image thing I'm talking about. But here we don't know where the maximum is. So we have to take every instance of x in this equation, this one, and mirror them all. So it's easy enough to do. Let's just copy our equation and change it by, instead of the variable x, we're going to do L minus x. And now, whenever we put in x equals 0, so that should be the left end of the beam, this will come out and there will be an L right here, L minus 0, so that'll actually be L. which is where's we at? Which is this side of the beam right here, where the roller's at. But when we mirror that, that is the left end of the beam. So when we put in x equals 1, we'll have L, which is L was the whole length of the beam, 14.4 feet, minus 1, so that's 13.3 feet, 13.4 feet, which is, you know, just right over here somewhere. But when we mirror that, that's just 1 foot in from the left side of the beam. And so we have to mirror this equation, and it's still only good, this equation, even mirrored, is still only good from 0 to the point load on the longer side of the beam. So it's only good in this side of the beam, which when mirrored is the right hand side of the beam. So there's a lot. This is probably the hardest part of all of beam deflection, is dealing with this thing when you have to mirror it, and when can you use the equation as it is, and when do you have to do something like this with the L minus X. We have to do L minus X in this case because we don't know where we're looking. And so what I want to do is I want to create an equation that adds this equation, the mirrored and modified one, to this equation, and we find the peak, and we'll just use a trace on our plot to figure out where the peak is. So let's do that. Let's take our y total of x equals the new y, well, it's not capitalized, y2 of x. Now I already had a y2, but the way MathCAD works is the most further down the page is the one that's active. Or well, if I write below it up, if I write above it, then it uses this one. So it looks where you're at, and it looks up to find the definition, and the first definition it finds is the one it uses. So if I'm right here, it'll look up to this equation and use that one. If you don't want to deal with all that, just rename them to different things. Plus y1 of x. Okay, there's my equation. I'm going to plot it because I don't know where the maximum deflection is. So x will be down here. I think must have caps long. There we go. I'm going to use units of use feet, and then this will be y total of x. I'll use units of inches. Got some weird things, some weird shapes going on here, but it's plotting out way out here at negative 40 feet. So let's change. Our equation is only good from x equals 0 to x equals 6.4. No, 0. No, it's actually only good from 6.4 to 8. The way that we've mirrored the beam. Not 8 to 14.4. Super tiny. Let's make our deflections like they're not going to be 0.1 maybe to negative. Well, just a 0. There we go. Now again, my deflection should actually be negative of this because I've used both of these as positive, where technically they should be negative. So I will have to add a negative sign at the end. So now I can see that the maximum deflection is somewhere right in here. So if I add a trace somewhere around 7 feet. I'm going to zoom in on this section. So basically I'm going to change my limits to 8 here, and 6.4 is fine there. All right, so now we're much closer. And we have 0.4, so let's change our maximum to 0.5, and our minimum can stay at 0. Well, it doesn't like that. Let's make our minimum, looks like 0.4 can be our minimum. All right, so now we can kind of begin to see where this peak is. I don't know what it is defaulted to my step in X direction. It's pretty big actually. So let's override that. Let's say that X is going to equal, we're going from 6.4 feet to 6.4. Let's count by, I don't know, see if we can get really small increments here. I don't know if it'll let us do that or not. Sometimes it has too many points and it won't plot them. Let's see. Not plotted. So we're counting by hundredths of a foot. So that's a weird unit, but that's what we're doing. So what I want now is I want to find where the peak is. So I'm looking at the Y value. Y value is actually not changing. So there's a 0.19. So 0.19 is the peak, but it's kind of flat in that peak, at least for the equations that I'm dealing with. So I'm definitely sure WebWork is not going to like anywhere from, where does it start? All right, so there, 6.993 to 7.036. Let's just take the average of that and we'll use that as what we put in. So 7.036 plus 6.993 divided by 2, 7.0145 will be our X position. And then the Y value right here, 042418, that will be our amount of deflection. So this is one way to do it. You could do it with calculus. Like I said, take this same equation. Well, the equation that is created by adding these two together, take the derivative of it, set the derivative equal to 0, solve for X, and that would give you somewhere around this same 7-foot number. So where did... There we go. WebWork. The X location, I had 7.0145 feet, and the amount of deflection I had minus, oh, I don't know, I didn't write it down, 042418. 042418 inches. It actually liked both of those. So great. I don't know why we were off, or why, actually this first one, I don't know why I counted it wrong. Second one, we're off a little bit. I'm not sure why. Third one, we're off 300ths. So that's, I'm not sure where that's coming from. I really suspect that there's some little decimal in here that WebWork knows, but it's not showing me. It's just rounding it somehow. I don't know any other reason that it would give me such a different answer. But we at least got these right. And this is the one I thought we would be most likely to get wrong. So just to go back over what we did with that. Well, let's see. Here's the equation of the elastic curve for the distributed load. It's pretty ordinary. There's nothing, even if we mirrored it, it would give us the same thing. So it doesn't matter. Here's the equation of the elastic curve as given in the book for an eccentric point load, which is fine. It only operates in a certain section of the beam, and that is the longer section. So the distance, the side of the beam that's further away from the point load, this equation only works there. We had to take that equation and mirror it. That's the L minus X part in this equation. The equation is exactly the same, except everywhere there was an X before, I replaced it with L minus X to mirror the equation. And then I plotted it. I zoomed in on the limits. You know, this equation isn't even going to be good. Even though the distributed load equation is good from the whole length of the beam, the eccentric load is only good on the 6.4 to 14.4 part of the beam. So I can't, anything beyond to the left of 6.4 feet is not accurate when I add these two together. So I zoomed in on that, found where the point maxes out. Now I suppose I could zoom in much closer and really try to find where it peaks at, and you know, try to get better resolution. I don't think I'm going to get any better. Yeah, it's the same set of numbers as I had before. But basically, I was watching this Y value where it peaked at. It peaked at two different places, depending on if you're approaching from the left or right. And I just averaged those two places to get the number we put into WebWork. Obviously, you can't do that on an exam, and I'm not going to ask you to do something like this on an exam. It's even though it would be technically possible, it's you'd have to do it with calculus, and it would be quite a tricky thing to work through in the format of an exam. Maybe a take-home exam or something, but not a timed exam. All right, that took us plenty of time. We're at 12:50. Let's look at the next one here and see if there's anything we want to do with it. So we have metric units. This one has the cantilevered sections. We did do one of these. Which one did we do? It might have been one of the option. Oh no, we did this one. Where there was a point load on a cantilevered section, and you have to treat that, for most cases, you treat that point load as a moment. So a moment here, F times B at point B. So this force times this distance is the moment at B. And that works for most things. It did not work for part C, because that one, if you apply a moment here, this part of the beam BC would just be deflected. It would just be angled downward. But there's really a point load on the end of it, which makes it bend the entire length. And so we worked that one. This one that I was looking at just now has two of those. It has this exact same thing on this end, and then over here it's got a similar thing, except it's a distributed load. So for the distributed load, you have to lump it, create the moment by the lumped load times half of A would create a moment about B. So that would work for part A. For this part, the deflection at A would be different. That one you'd have to do basically the same thing we did last time, where you angle the cantilevered section AB, and then you bend the cantilever section AB based on that distributed load across it. So you would have to do that. Slope at point C, that's ordinary. Deflection at D is the same thing that I just described, except with a point load. So again, this thing with 5 parts to it, definitely not a test question. The test questions you'll probably have 2. One of them will be very straightforward, no mirror images, nothing like that, just a straightforward beam deflection. And the other one will have you use superposition. I don't know if it will have you use change the force into a moment, or use the arc length type calculation to calculate the deflection. I don't know if it use one of those, but it will have something to do with superposition. I don't remember yet what it'll have. All right. I'm not going to do any new homework yet. Homework 18 will come out once we talk about torsion. And so we'll talk about torsion, I guess, tomorrow. Let's talk about the Truss project for a bit, and then, unless I see some questions pop up, we'll probably end a little early today. So I know this says 2020. I just used the same one because it worked pretty well. When you look at not Blackboard, we haven't used that in years. When you look at Moodle, you will see Truss project overview. You'll see it's labeled 2021. You also see 2 other links here that we'll talk about. So here's the idea. We are doing a simulated truss project because not everybody is anywhere near town. You're not going to necessarily be able to come pick up supplies or do anything like that, and come test it or anything like that. You might be able to, but not everyone could. So this is what we're doing. You can still use a group. So you can have up to 3 people in your group, even if you're all remote to each other. That's fine. I'm not going to define the truss structure as far as it has a certain span and it has a certain width or anything like that, height. It just needs to be a truss. So the only rules are that it has it's statically determinate, so it is something you can solve. Basically, that boils down to you don't have any joints with like 6 different things connected to it, because that's going to end up being indeterminate. So it does need to be statically determinate because you need to solve it by hand. And then you're going to also solve it through simulation. I have written that you will analyze it in SolidWorks. If you have a different piece of software that you already know how to use to analyze trusses, then that's okay. If you have nothing, then use SolidWorks, because you do have SolidWorks, or at least you can get SolidWorks. So like I said, the thing could be anything. Just a tray. Most people are going to default to a truss bridge, which is fine. It doesn't have to be anything spectacular. I would definitely suggest it be a 2-dimensional or planar truss, even if it's a series of planar trusses, like a bridge would be, that has 2 sides to it. But I would not do a 3-dimensional truss, just because the hand calculations on that would start to get cumbersome to do, and probably not worth it for what we need out of it. You're going to turn in a written report, and then here's the format for the report, basically each of the sections that go in it. You are setting your own design objectives. So if you want to build a truss, a bridge type truss, or design one, not build it, you don't have to design these to the level that somebody could actually go and make it. You just need to design in SolidWorks something that represents what you're going for. Tomorrow we will also I'll go into SolidWorks and show you some tools that you can use in SolidWorks to do the analysis part, the simulation part. It has truss finite element analysis built into it that you can do, and so I'll show you how to do that. And you can build it through an assembly if you wanted to, and it can do that. It'll take a long time to calculate, but you can do it. So you set up the design constraints as far as this needs to be 50 foot long, and it needs to support this kind of load, that kind of stuff. You set those own design objectives yourself. That way every team can create whatever they want to create, and you're not really trying to do the same thing. What materials are you using? If this was really being made, again, it's only simulated, so you don't actually have to go fabricate the thing. You'll come up with some alternatives once you've set out your materials that you want to use and your constraints on the problem space. Then you propose 3 or 4 alternatives for what might look like a good solution. These don't have to be completely worked out. These could be like sketch level, neat sketch level alternatives, and then a little reasoning, not just a guess, but a reasoning of why you want to go with the chosen design over all the other alternatives. Then you'll do calculations. So this is where you'll go in by hand, do method of joints, method of sections to figure out the member forces. And when they'll fail, I'll also go through a spreadsheet, I guess, of how we can predict where it's going to fail based on different failure modes. And then you'll build the thing in SolidWorks, do the same analysis, see if it predicts the same thing. Then you'll have a little bill of material. This will be, if you were to build it, here are the rough cost of what it's going to take. You don't have to get into like nuts and bolts, but in the bulk material. So I would recommend something that's reasonable sized, not an actual vehicle bridge, because it's going to be harder to estimate the cost on that. Something that's reasonable size would be better. And write up a little conclusion, whatever references you use, and then appendix will have design calculations, maybe MathCAD sheets or something like that. Free body diagrams of everything. You should have like a sample of this in your body, but the appendix will have the full worked out, like a homework problem type thing. So that's all spelled out. You can have 3 people on your team. These links are, we'll get to the buckling later. I'm not going to talk about it just yet, but this is a mode of failure that we don't really cover in this course, other than as part of this Truss project. So I'll talk about that in its own thing separately. MD Solids, I think I mentioned it before. This is a free now calculator tutorial that does a lot of different things related to mechanics of materials, and I really like it. Its interface maybe is outdated, but once you're used to it, it does a lot of stuff. It can do shear and bending diagrams. It can do moment of inertia calculations, Moore circle, which will mean something if you go to the next statics class, pressure vessels that we're doing soon. All of this stuff. There's column buckling, and it will analyze, well, not analyze, it will calculate the member force for statically determinate trusses, and you just draw the truss on the screen. So you go to download it. Here's the registration code, and it opens it all up forever. It's not a free trial. You get the whole thing forever. So it is a nice little package of stuff. Torsion is in there. That's what we're about to start doing as the last third of the course too. The other one I clicked or linked is that buckling calculator. It's just an online tool for calculating column buckling, but we'll talk about that by itself later. All right, I didn't see any particular questions pop up in the chat, so tomorrow we will come in, start our torsion. I'll also show you some SolidWorks things. If you still are having questions with beam deflection, particularly if it's this one that we worked, not that one. Yeah, that one. It looks like there might be something in the way it's displayed that you just can't get the question right. So if you're pretty sure you're doing it right, then email me and I'll be able to see if you're just off by the same, 10,000ths of an inch that I was off by, and WebWorks just being picky. I did make this problem set due later. I think it's not due till Saturday now, or maybe Sunday even. I don't remember. All right. I will see y'all tomorrow. We'll do some SolidWorks. Oh, wait. I did get, remember last time we were doing SolidWorks beam deflection. I did get that to work. It was a really simple fix. I'll show that tomorrow also, because it's I don't have SolidWorks running right now, so it'd take a while for it to boot up. But it was a really simple fix. I basically added a pin, rounded pin shape onto the end of the beam and constrained that as a pin, and it worked fine. So it did not give me the same predicted value that we calculated with the equations. I think it was, I don't remember the numbers. I remember 20 and like a 12. I don't remember if that was 0.12 or 12 inches, but or millimeters or whatever it was. But it did give us in the ballpark, but not exact. They weren't the same. Any type of curve on the test. So I haven't graded all of the partial credit, and so the grades will change. I wouldn't call it a curve because that's a different thing. The grades will change and they will go up. But I haven't done it all yet, so I would expect 5 to 10 points. Everybody's will be different based on your partial credit, but 5 to 10 points up when I'm done with them. That was a question in the chat. All right, we'll come back Thursday and tomorrow and do some SolidWorks and a little bit of torsion intro.